All right. Thank you for attending the USPA webinar. My name is Ming Xiao. I'm the president of the USPA, the U.S. Permafrost Association, and also a professor of civil engineering at Penn State. Today, Oliver Hoops from Shannon and Wilson and will present an engineering case study, Trans-Alaska Pipeline Lost Lake Thermal Improvement Projects. And this actually is our eighth webinar the USPA has been organizing, and the last one in this year. In the 2025, the USPA plans to organize eight other webinars of different topics, and I'll share that with the audience. Well, the format is same as before, and we'll have a few minutes of a brief introduction, and then and the lecture is going to be about 45 minutes, and then we'll leave about 15 minutes in the end for question and answers. Although you won't be able to share your audio or video, and you can type in questions by clicking the Q&A button, and throughout Oliver's presentation and talk, you can feel free to type in the questions. Yeah, and you don't have to wait until the very end. Okay. And um, the webinar is going to be recorded, and after that, the recorded link and the PDF format of the presentation will be shared with you. If anyone needed the professional development hour certificate or PDH, and please email me, and then I'll send it to you. Okay. Um, well, the USPA webinar series is sponsored by Arctic Foundation's Shannon and Wilson, P&D Engineers, Geo Watershed Scientific, BD Stream, and individual sponsor Catherine Scheckneider. Just a quick introduction of our instructor and speaker today. Uh, Oliver Hoops is a geotechnical engineer at Shannon and Wilson, with PE licensed in Washington and Alaska. His expertise includes slope stability analysis, thermal modeling, risk assessment and mitigation of landslide hazards, soil characterization, geosynthetics, soil improvement design, liquefaction analysis, experimental soil mechanics, and geotechnical report preparation. Really are a wide expertise and experiences. Oliver currently serves as the technical director of the geotechnical laboratory in Shannon and Wilson's Seattle office, and is Shannon and Wilson's corporate practice lead for risk and reliability design. So with that, and thank you so much, Oliver, for sharing your time and your expertise with us. And then I'll leave it to you.
Okay, thank you, Ming. I'm going to be talking about the Lost Creek Thermal Improvements Project. It's definitely, I think, my favorite project that I've done here since I've been at Shannon Wilson since 2007. So let's get into it. Quick outline. First, I'm going to go over the background of the site, the problem statement, basically. Then I'll go into the design approach. Then I'll get into the thermal modeling that we did. And then I'll go over the construction and long-term monitoring, the post-construction long-term modeling. And then now that we have this post-construction data, we're able to make some comparisons and see how our model did. So background. The Lost Creek site is about 60 miles northwest of Fairbanks. So Fairbanks is right about here. Go up the Dalton Highway a bit, and you'll find Lost Creek. Just a really quick overview of TAPS. Most of you probably know this, but I'll summarize it anyways. It's 800-mile pipeline. It goes from Prudhoe Bay, the very north of Alaska, down to Valdez. About 420 miles of the pipeline is above ground and 380 is buried. It's a 48-inch diameter pipe. there's about 78,000 above ground pipe supports, or vertical support members is the term that's used for those. And over half of the VSMs are thermal, so they have passive thermosiphons in them. So here's the site. It is a west-facing slope. So north goes off in this direction approximately. When they originally constructed this, they achieved their grade for the pipe by doing a big cut up here at the top of the slope and then using that material to fill an embankment down at the base of the slope here. And then just for reference, there's 3 clusters of instrumentations, inclinometers, thermistor strings, primarily, and I'm going to be referencing these for the next for a lot of the presentation. So that's where they are. Okay, so the problem statement. When they constructed this, it was in the winter. They filled over this area down here, and it turned out that that was a peat bog. So it was frozen, so it held up during construction, but ever since then, it's been kind of gradually warming and thawing. And a shear zone has developed in the frozen peat and the slope fill, and it started moving shortly after construction. Slope movements have been exacerbated by permafrost warming. And so the real consequences of that slow creeping movement is that the pipe supports are starting to tilt. And as if they tilt too much, then it becomes very hard to maintain them. So after about 3 degrees of tilt, it kind of becomes a problem. So these vectors are tilt magnitude vectors, and the size of the arrows corresponds to the amount of tilt. So you could see that a lot of the VSMs were tilting down towards the creek pretty excessively and pretty uniformly down here, at least. And then we also had some shoulder rotation along this southern slope, the southern part of the fill slope here. It's kind of more like settlement than shoulder rotation, but it looks like effectively it looks like shoulder rotation when you're out there. So those are the 2 kind of main problems that needed to be addressed. Okay, so here's a geologic cross sections through the slope. This one on the left is along the pipeline. The one on the right is a transverse cross section down here where the peat is the thickest. The frozen peat layer is this brown material. And then here's where the shear zone was identified based on inclinometers that we have throughout the slope. We have quite a few borings out here, so we have a good bit of lab data that we had to play with for preparing soil properties, and as you can see, we had pretty variable water contents. This is a log scale here. Yeah, so in those instrumentation clusters, they were measuring fairly uniform displacement rates at about a half an inch per year in the shear zones. That's what this plot is here. Our measurement started in about 2006, and then some more instruments got added later. Okay, so diving in to the inclinometer data a bit more, these plots show the cumulative displacement between 2009 and 2020 near the bottom of the slope. We see we have about 5 inches during that time. This other cluster, it goes from 2006 to 2018, and we got about 7 or 8 inches during that time. Thermistor data, you can see the 32-degree isotherm here is this dashed red line, and we're just right below it in the peat layer, which is these brown layers. So pretty warm permafrost. Another view of the thermistor data. So this data is for the top of the permafrost. So we're looking at the temperatures near the top of the permafrost with time, and you can see kind of a gradual trend upward here, especially near the end here and after 2015 or so, 2018 or so, starts to kind of keep going up, which was not a good thing to see. Okay, so the design approach. This slide here kind of summarizes the whole design situation here. So we have an overall design criteria of 3 degrees of VSM tilt over the design life. And at the time that was 40 more years. So 3 degrees in 40 years, that was a design criteria. Temperature in the peat, that's the main thing that we could control, and we in order to achieve that. So we had to develop a series of relationships in order to show that reducing the temperature here can let us achieve this. So we used strain rate lab testing that the University of Alaska Fairbanks lab did to relate peat temperature and rate of slope movement. And we used the long history of inclinometer and tilt data to correlate those two things together, and then we kind of aggregated all the data and strung together the correlations to make this work in summary. So our main tool for cooling is freestanding heat pipes or freestanding thermosiphons. And maybe even more importantly, wood chip thermal surface insulation. I'm sure most of you know how thermosiphons work, but I'll just give a very quick summary. They are completely passive, so they have no moving parts or supply power. Basically, you have a very low boiling point gas working fluid inside this sealed pressure vessel, which is the heat pipe. And there's a condenser at the top, which are these fins. that allow heat to radiate out, and as that heat gets removed, the working fluid condenses and it falls down to the bottom where it will extract heat, collect heat from the surrounding soil, and then it will boil again, and that process cycles as long as it's cold enough outside. Okay, so UAF lab testing. So they came out. This is Peppy Croft from Shannon Wilson at the time, out here collecting some high quality samples of frozen peat using their special tool. Here's some nice pictures of the frozen peat from the UAF report. So they did transient creep testing on the peat cores. So these are fixed. They have fixed temperatures and variable strain rates, and they're able to make these relationships. So that this data allowed us to develop relationships between shear strain rates, temperature, and shear stresses, which we use for design. And our analyses showed that if we could cool the peat to 29 degrees or lower, then we would achieve our target tilt of 3 degrees in 40 years. So that 29 degrees, that became our target. Okay, so thermal modeling. This site is pretty far from a good, reliable NOAA station. I know there are some prism models that you can look up historic data or make a synthetic record. We did not go that route at the time. Instead, we decided to come up with a composite air temperature record by piecing together the closest actual data and combining it into one record. So we have one instrument on site that's active now. It only goes back to, I think, 2008 or so. And then we had a couple of other NOAA sites, and then we did end up having to backfill with Fairbanks data. Our model we had a 40-year spin up. So we went from 1980 to 2020 using daily time steps, and we used a 5-day rolling average smooth temperature data set, and that smoothing process helped the convergence quite a bit. And then post 2020, we applied monthly temperature increases based on the SNAP RCP 6.0. So we had a synthetic sinusoid, temperature sinusoid that we gradually ramped up with time. So we still continued the 1-day time steps using the synthetic sinusoid. We started the modeling process with a series of 1D calibration analyses at 2 locations, one at the upper slope and one near the lower slope. So let's see, we've got the measured thermistor data points are the the circles, the empty circles, and the modeled temperatures are the solid lines. So this is one of my favorite, these are some of my favorite plots for the project because we were just really pleased with the ability of the model to predict, to match these temperatures. And so it matched the 2018, 2014, like we checked quite a few different dates with actual thermistor data, and they all kind of matched pretty well. So this gave us the confidence to that our soil parameters and our boundary conditions and everything was working correctly, and then that gave us the confidence to move to the more sophisticated modeling. So in the early part of design, we did not have Temp 3D available to us. So for the preliminary design, we used a combination of plan view analyses, 2D analyses, and axisymmetric simulations. Right here, what you see is some 2D analyses. We mainly use these to look at the shoulder rotation issue at the toe of the slope. And so at first we were looking at 5 rows of the thermosiphons at a 12-foot square pattern, and that's kind of shown here. We've got and we had wood chips that, based on these preliminary 2D analyses, we found that we had to, if we tried to end the wood chips at the toe of the slope, then our temperatures would it just wouldn't be enough to cool to keep the slope cool. As you can see, the temperatures were very high near the toe of the slope. But if we extended the wood chips out by like about 30 more feet, we would get much cooler temperatures in the at the toe. So for the preliminary design, we did have this big extension. Unfortunately, that was into a wetland down here. And also it would have required shifting a small creek down there, which was not great. Also, yeah, as a reminder, so the 2D analyses, you can't model vertical thermosiphons in 2D. It's just geometrically does not work. So to get around that, we did a series of 2D plan view analyses. These were helpful for rapid layout evaluation. The peat layer for this site is deep enough that this approximation was not too bad. But we did end up doing some calibration against axisymmetric simulations, where we did model the thermosiphon vertically in an axisymmetric cylindrical kind of coordinate system, and that the result of that calibration convinced us that we need to reduce the thermosiphon conductances just for the purposes of these models, these 2D models, by 40%, and then that kind of got them to be roughly equivalent. Okay, so Temp 3D became available to us in time for final design. And so we developed a 3D model. This is what it looks like. The So it's a slice, it's a transverse slice through the hill. So this is the southern toe of the slope in that wetland area. This is to this north is in this direction, and right now we're looking downhill in terms of the pipeline. The width of this model in this direction is the half spacing of the thermosiphons, and the thermosiphons here are modeled. Half of them are modeled on this face here that you can see. So each of the faces are planes of symmetry. So this allowed us to model the entire array. So we looked at three main cases for the 3E. Case one, we looked at 5 rows of thermosiphons at 12-foot square spacing. Case two was 5 foot at 15-foot square spacing. Case three was 4 rows at 15-foot spacing. And this is right here. This is case three. A snapshot of that analysis. This is a cool little video of the results. I'll let this go a few times. So right here we're seeing the 5 rows, and then now we're seeing the 4 rows. The light blue, the cyan, that's our 29 degree isotherm, and the dark blue, that's 32 degrees. So the model is showing that we definitely do achieve the 29 degrees and cooler. Let's see, this plot over here are various vertical query lines in the model. Those are shown here. So that we got a red one and green's in the middle, pink. The dashed lines represent the face of the model that's midway between thermosiphon rows. That's this top plot here. The bottom plot is right at the cutting right through the middles of the thermosiphons. And that's represented by the solid lines on this side. Okay, so with all those strain rate lab testing and tilt data relationships, we were able to take the modeled temperatures with time and numerically integrate them, and numerically integrate the strain rates over time to end up with displacements. So each of these colored lines represents a node in the model that in the peat. And so as you can see here, we're this is pre-treatment. The treatment starts about right here, and then after that point, obviously everything starts to cool quite a bit, and up until let's see, treatment starts here. So this is post-treatment shear displacement. So T0 is here in terms of treatment. So until everything cools sufficiently, the model is showing that we'll still continue to see shear displacements until the elements get cold enough where it just the movement should just stop because it's just too cold to move. So that's why we have this ramp up and then plateau because it's just too cold to move. So this pair of plots on the left are the 5 rows. On the right, this is the 4 rows. And this plot here kind of convinced us that we really don't need the 5 rows. So at this point we realize let's just only look at 4 rows, 15-foot spacing, 4 rows, because the difference in displacement is negligible. So overall conclusions of the model, 4 rows of thermosiphons at the 15-foot spacing, is saying that we should achieve all the peat should be less than 32 degrees within 2.7 years, and then all the peat within 20 feet of the center line should be 29 degrees or less within 3.5 years. So that's kind of the time frame that we expected. Some other benefits so the 3D modeling really helped us. It allowed us to get rid of a bunch of peat, a bunch of wood chips extending into the wetland area here. It meant that we didn't have to try to move this creek. We reduced to 4 rows of thermosiphons, and we increased the spacing to 15 feet. That kind of all came about by moving to the 3D modeling. All right, construction. So gonna go through a bunch of cool pictures. This is aerial photo during construction. So this is early grading. North is to the left again. Thermosiphon drilling. So the way these are installed is they drill a casing into the ground, and then they lower the thermosiphon pipe down in with some stabilizers, and then they backfill it with this with silica sand and water mixture, so it's like a sand slurry, and then that freezes, and that's how they're installed. And so this is one of the drill rigs, installing one of them. We definitely found peat. This is from the drill cuttings. So it is frozen, even though it get kind of hard to tell from the photos that it's frozen, but it is. More casing drilling, colder this time. Here's the that south face that's basically complete. They at this time they were still drilling on the north side though. Here's a photo of them lowering a thermosiphon down into one of the casings. They had a crane on site. Here's a nice completed aerial photo of the project. Again, north is in that direction. Another nice photo. I think this was taken 1 or 2 years after construction. So one thing that's nice about the wood chips is that they last for a long time, but also their albedo improves over time, as you can see. Okay, long-term monitoring. We installed 3 new clusters of instrumentation in 2022, shortly after construction. So we have these 3 points right here in the mid span between thermosiphons. And then we also had this older cluster that we were able to save, so the data from that continued. We weren't able to save the other 2 older clusters. So okay, so this upslope older cluster here, here is the temperature data. We have construction completed right about here. You can see that we had massive cooling. This part of the plot, it's warmer. It appears warmer than it actually was. We didn't have a data logger on this machine. We didn't have a data logger taking real-time measurements prior to construction, so these represent like spot readings, and it's biased towards the time of the year where we could access the site easily, so it looks warmer than it really was. So see, oh, this is just the same thing but zoomed in post-construction. Okay, so construction completed about here, and then you can see there's one winter, there's a second winter, there's a third winter. So it is getting colder and colder, and it's getting super cold with time. All right, so new thermistors. This one is the one that's furthest south. It's right about here. We have just 2 winters worth of data here, looks like, that we're showing. It is getting colder. But one thing you can see is that look at what happens to the active layer depth. It's just really, really, really reduced. Basically, it's the active layer goes up into the wood chips essentially, which is great. Here's the next one over, the second one. So this one's closer to the middle of the array. You could see it's getting quite a bit colder with time, and it's getting, yeah. Same thing with the active layer. It's pretty shallow active layer. And then this one is the furthest north, and even colder, the coldest one. It's very cold. Okay, so how does this compare to the model? Let's take a look. So this plot, so we're plotting all 3 of these data from all 3 of these locations. The green little bit of data is from the thermistor readings, and this is taken at the thermistor node right in the middle of the peat, and then this brown curve is the model, the corresponding location in the model at this boring location at that same like middle of the peat, right in the middle of the peat location. So you can, as you can see, it's we're getting a lot colder than the model showed. We're we're essentially already there. We've already achieved the target uh, at all three locations. So this is our 29-degree target here. So we're 4 years ahead of schedule for this location, 2 years ahead of schedule for the other locations or thereabouts. We've also got the inclinometer going out there. This guy right here. It's kind of hard to tell that the trend. The trend is kind of towards increasing displacements, but also like it kind of went a bit and then it went back a bit and then went out again. So but overall it's still all less than a quarter inch of ground surface displacement. And just for reference, right about at this point, the model was saying that we should be about 3/4 of an inch. So we're doing better from a displacement perspective as well. As kind of a summary, we use 3D modeling, transient thermal creep testing. We were very proud of how we were able to be environmentally sustainable by nearly eliminating wetland impacts, providing long-term cooling without the need for supplied power, moving parts. We reduced waste by not constructing nearly as much as we would have by going to the 3D. We improved resiliency of taps. This was a big risk site that had been on the books for Alyeska for many years, and reducing the risk for the site was huge. And we had related to all this stuff, we ended up achieving a pretty some big cost savings from reducing a bunch of stuff. So that's it. We have some extra time for questions.
Thank you, Oliver. There are two questions currently, and if you can click the Q&A and you can see the questions. In the meantime, our attendees can feel free to type any other questions, if any.
Trying to find I can see chat. Let's see.
Yeah, if you go to
Oh,
Q&A, instead of not chat, but go to
okay.
Q&A.
Okay. All right. Got it. Okay. Anonymous attendee says, have freestanding heat pipes been used for other pipelines? It's definitely, we've used it for taps before. Uh, at quite a few sites. I'm not sure about other pipelines. Yeah, I'm not sure about that.
Oliver, if
Yeah,
since we're recording it, and I don't know if the questions can show in the recording. So if you could read the question first and then provide answer, that'd be great.
yeah.
Thank you.
So how thick is the wood chip layer? Is there any maintenance required? Okay, yes, the wood chips are 3 feet thick. In terms of maintenance, we have assumed that at some point they might have to go out and refresh, but there's some wood chip sites on taps that the wood chips have been there for, I don't know, 30 years maybe, and they're still working. And they have an increased albedo now because the color is they're basically white. So yeah, I think Alyeska does know that they will have to refresh at some point, but they're really great material. Okay, so next question. Do you think you could get away with fewer thermosiphons than the modeling suggested? Yeah, for sure, yes. We could have next time, I don't know. So Alyeska is happy with the amount of cooling. They're happy with overcooling. I think that handled the shoulder rotation issue a little bit better than what we hoped for. That said, yeah, there were definitely some things that we were pretty conservative about. One of them was we don't typically don't account for wind in the thermosiphons. So if you account for wind, you might be able to show that they work quite a bit. So yeah, we probably could have got away with less thermosiphons for sure. Yeah. What was the source of the wood chips? Were they produced on site or imported from Fairbanks? They were imported from Fairbanks. They were from Northland Wood. I think that's what they're called. They're basically a wood waste product. We didn't cut down any trees on the site to do this, that's for sure. How long do you expect the wood chips to be effective? Again, we've had some sites for over 30 years, I think, and maybe Frank can chime in if that's wrong. But I think there's some sites that they've been there for decades and they're still fine. Thickness of wood chips, that's already answered. Okay. Oh, I see. Chuck Schultz. Hi, Oliver. This is Chuck and Frank. Thermosiphons are commonly used for pipelines on the North Slope. Okay, so that answers one of the very first question. So yes, they have been used for other pipelines. Thanks, Chuck. Question, were insulating materials other than wood chips considered? Yes, we did briefly consider other types of insulation like buried polystyrene. That material is just it's construction is kind of a nightmare, especially on a slope. So you'd have to stair step it. It's just also a lot less sustainable than using the wood waste material. And I'm not really convinced that it would work all that better, actually. Let's see. Next question, Trevin. Oh, hey, Trevin. I know that guy. Do you think the wood chips alone would have met requirements with post-construction data? Hmm. It's possible that wood chips alone could eventually get there, but that would be you'd be taking quite a risk. I don't know if that's a risk that somebody should try that somewhere else, not on a slope that supports taps. Next question. In your displacement models, what exactly are you modeling? And do you think increase in rainfall as project with climate change is going to impact your site's efforts? So we're not modeling displacement, we're only modeling temperature, and we're using the relationships from the UAF lab testing to relate temperature with strain rate. And then we integrate that over time to get displacement. Rainfall, do I think rainfall? Increased rainfall, it could. We definitely didn't consider that. Yeah, I I have to think about that some more. I'm not worried about it, that's for sure. But with the amount of cooling that we have. Next question regarding the geometry of the thermosiphon as it plays a critical role in its thermal performance. Could you clarify the dimensions, condenser to evaporator ratio of the heat pipe and explain how they were determined? So that we used, I think we just used 4-foot fins, and the embedded portion of the heat pipes were very deep for this site. They went down, I think they were about 60 feet on average or so. We originally thought about like insulating part of them, like the upper part where we didn't really, because we wanted to target the peak, but then in the modeling kind of showed that that didn't really help. So so we didn't end up doing that. We did some analyses to figure out whether to use, essentially Alyeska has fins on hand, and we had either 6-foot or 4-foot to choose from. So we worked with what we had on hand as well. Okay, Chuck Schultz says that we expect to replace the wood chips every 15 to 20 years. So thanks, Chuck. Chuck is with Alyeska Pipeline. How effective were the wood chips at insulating on their own? We kind of already talked about that one. Was any strain relief needed even after the cool down? I'm gonna have to ponder that one a little bit. I'm thinking no, but I'm not 100% sure if I understand what you mean. Trevin said understood would be cool to back analyze. Okay, that's in reference to his earlier question. Okay, that's the end of the, oh. Chuck says, can you unmute me? I haven't actually heard you. Oh, unmute. Oh
Yes.
yeah. Can you unmute
Yeah,
Chuck?
let me do that. Let me see. Okay, hang on. So in the meantime, and Vladimir, you have your hands up, and if you have anything to comment.
Oh, thank you very much. Very good presentation, Oliver. It's Vladimir. I have a couple questions about modeling. It seems like from what you showed, you choose to have temperature at the bottom of your model prescribed and constant. Do you think if you will let it change, you will have a little bit better fit of your model predictions and
We didn't have a constant temperature in the bottom. We had a constant geothermal heat flux?
Well, it seems like from the temperature profiles you showed, your bottom temperature was sitting at the same point when your other, or it's just seasonal changes, right?
Let's see.
Yeah, there is some temperature profiles was shown as a result of modeling.
Yeah, the bottom temperature
Yeah,
doesn't
see,
change that
see
much.
how it's holding when you it
Yeah.
goes. Yeah, see the green line? It tried to go to the left, but the bottom holding it.
Mm.
See right there. So yeah, of course it's pretty deep, so maybe it will not have that much effect on the upper temperature regime, but it may actually be a little bit cooler results in the model if you just let see what I see.
Mm.
It's not zero flux. It's like temperature is fixed on the bottom.
Yeah, it does look that way.
Yeah, but like I said, maybe it's not that big effect because it's pretty deep compared to where you're looking for the temperature change.
Mm.
Well, and second one, for again, when you compare what happened in reality is temperature and what was predicted, you may predict maybe warmer ground temperature or air temperature, whatever you put in the input model, than it was, because it was actually cooler. 21, 22, 23, it were relatively cool years. So it may
Okay.
actually make your model prediction a little bit closer to what you measured.
Yeah. Okay.
Thank you, Vladimir. So yeah, Chuck, feel free to add, please.
Jeff, you're still muted if you're. Oh, there you go.
Hey, thanks, Oliver. That was a great presentation. Hey, I just a couple of questions that people had that I think, you know, I would say on the does rainfall affect it? We're semi-arid, so the peat layer being as deep as it is, and getting as cold as we are, I guess we wouldn't expect to see a major impact from increased precipitation. Um, as far as uh, did we need to do strain relief in the pipeline? From the pipeline side of things, right? The pipeline is sitting on shoes that are allowed to move freely on the cross beams, cross members of the supports there. And so, as we did do a project before this to replace the piles that had been pushed over with 40 years of movement, right? To so we did a reset those to vertical, essentially. But because the pipe is decoupled from the supports, there isn't a huge amount of strain induced in the pipe from the ground movement, and that was per design. So no, we didn't have to do strain relief, but we did reset the supports to be vertical.
Chuck, have you ever had to replace any wood chips yet? And what's the site that has the oldest wood chips again?
Is it the um,
Glutina, maybe?
I think it's Clutina Hill, and I don't recall exactly how old these are. I mean, they're gonna degrade over time, and we fully expect to have to refresh them or add to them, and just from planning purposes, 15 to 20 years. They're really a great material. They seem to be lasting a long time. When we get them, we try to make sure that they're clean, have a little bit less bark and things like that would add to the decomposition. And the other, there's a question about, did we consider other insulation techniques? And we have, and historically we have a lot of buried board insulation, and it's really a nightmare when you get ground deformation and it starts to break apart, or if you have to go in and do a repair, you have to dig through it, and then you have to try and repair it and put it back. And so the wood chips are very forgiving from conforming to the ground, and being able to push them to the side, do your work, and then put them back. So it's really been um, just seems they're we haven't really seen a negative to them so much compared to the board type insulation. There was one question about, do we think we would have seen the cooling with just the wood chips? And I think, you might, if you were to go north, maybe you could get the kind of cooling here in Fairbanks and south. We really need, I think, that passive input from the thermosiphons. Could we have done it with fewer thermosiphons? Possibly. We're pretty happy with having some redundancy in the system and some additional factor of safety against climate change going into the future. But we wouldn't make it here in Fairbanks, I don't think, with just insulation. We need that passive.
And it will take a long time. You don't have this time.
All right. Hey, thank you. Thank you so much, Oliver, for presenting a very nice webinar for us. And thank you, Chuck, Vladimir, for providing further comments. So that concludes our webinar today. And thank you all for attending. And we'll be in touch. Thank you.
Thank you. Bye.
Bye-bye.